Let's start with definitions. What is a sound? A sound is a small and rapid fluctuation of pressure around a mean value. So we'll define these three terms: small, rapid, and mean value. When I talk about pressure, I mean initially the total pressure that is measured, for instance, in this room while I'm recording this video. And the mean value, the mean reference value, is the average over a sufficiently long time period of the total pressure. But in an acoustics course, most of the time I will not discuss the total pressure, which is basically irrelevant. I will just be concerned with the acoustic pressure, which is the difference between the total pressure and the reference pressure. So it is just the fluctuation around the mean value that is acoustically relevant. The mean value is usually the atmospheric pressure. But in fact, we may be concerned with acoustics in other media like water, and then the reference pressure would, for instance, be the hydrostatic pressure at a certain depth in the ocean. I say that the fluctuation is small. How small can that be? One way to consider that is to look at a very classical picture in acoustics, which is this acoustical thermometer from Brühl & Kjær. On the left side, you have the amplitude of the pressure fluctuation, and on the right side, we have something that we are not going to define today, but with which you are certainly familiar, at least aware of, is the dB scale used to measure sound levels. And so you have a match between a certain pressure fluctuation amplitude and a certain sound pressure level. And what we see here is that if you look at the very bottom part of the graph, you have barely audible sounds which are characterized by amplitudes of the pressure fluctuation which are of the order of magnitude of 10 micropascal, meaning 10 minus 5 pascal. That's very small indeed, because the atmospheric pressure is about 100,000 pascal or 10 to the power 5 pascal. So we are sensitive to pressure fluctuation as small as 10 minus 10 atmospheres. And then if you look at the other side of the graph, at the top part of the graph, where we are considering extremely loud sounds like the takeoff of a space rocket, we have levels of about 140 decibel, which corresponds to fluctuation of 100 million micropascal, meaning 100 pascal, which is still only a thousandth of an atmosphere, so very small indeed. The other thing to realize is that between the lowest, the faintest sound that we can hear, which is of 10 minus 5 pascal, to the loudest that we can hear, which is, let's say, 10 to the power 3 pascal, well, we have 8 orders of magnitude. So acoustics is covering a wide range of pressure fluctuation, but they are all very small in absolute value compared to the atmospheric pressure. Fluctuations are not only small in amplitude, they are also rapid. What does that mean? Look here at a recording, a stereo recording from a sound. The left channel is shown in green, the right channel is shown in red. And what you see, in fact, the white line represents the atmospheric pressure, and so you see that the pressure goes up and down, alternating moments where it is above the atmospheric pressure and moments where it is below the atmospheric pressure. You don't see it very well, but if we start zooming in, you see indeed features that appear in that signal. And if I zoom once more, you very clearly see that indeed over time the pressure goes up and down. It's not an absolute value, but on this graph the typical time of one feature of the signal is about 10 milliseconds, meaning that the pressure goes up and down 100 times per second. We have a signal that is roughly at 100 hertz. So that's indeed very fast. Now, definitions about acoustics. Acoustics is the science of sound, and in most cases we are going to consider propagation in air. But in fact, it can be, the sound waves can propagate in other gases like argon, krypton, xenon, for instance, in double glazing. But we can look also at propagation in liquid. We've talked about water already, but it can be oil, like in a transformer, or in fact any other liquid. It can even be propagations in solid, because in some sense the propagation of P waves in geodynamics is also part of acoustics. One more thing, acoustics is concerned with 4 different, let's say, sub-problems in sound. The sound generation, what is the physics of the source, what is the mechanism causing the sound. Propagation, how does the sound propagate from the source to the receiver? How does this receiver perceive the sound and records the sound? And then finally, although that's of less interest in classical acoustic engineering, sometimes the sound, while it propagates through the air or through water, is producing a lasting effect on the propagation media, and that would be the 4th part of acoustics. When you think of acoustical engineering, most of the time you consider that the work of an acoustical engineer consists in reducing the level of noise. But once you have reduced the noise sufficiently, you start being concerned with the quality of the noise. And so part of acoustical engineering is also about enhancing the sounds. So acoustical engineering is both reducing the noise and enhancing the sound, although we mainly talk about the first part in this basic acoustic engineering course.